All right, welcome to The Explainer. Today we're talking about something that's literally all around us, noise. From the city traffic outside your window to that open-plan office drone. But what if we could actually engineer materials that could tell sound where to go, or even better, make it vanish completely? It sounds like something out of a sci-fi movie, but believe it or not, the solution is very, very real. And no, you're not imagining it. As our research points out, all that constant, unwanted noise isn't just annoying. It's a real environmental stressor that actually impacts our health. Sure, we've built thicker walls, we've got better windows, but that deep rumble from a truck or a passing train, the kind that seems to go right through you, that low-frequency sound is notoriously hard to stop with the usual materials. So this is where the old ways of doing things just don't cut it anymore. And that leads to this really fascinating question. What if instead of just piling on more mass, more concrete to block sound, we could actually outsmart it? What if we could design materials so cleverly that they don't just block sound waves? They actually catch them, trap them, and stop them in their tracks. The answer lies in this totally game-changing class of materials. They're called acoustic metamaterials, and they're engineered to do things that honestly seemed impossible until pretty recently. Okay, so here's the secret. The magic of these metamaterials isn't about what they're made of. It could be a simple plastic or a metal. No, the real secret sauce is their shape. It's all about their incredibly complex internal geometry. By designing that tiny internal architecture in a very specific way, we can give them acoustic superpowers, like being able to bend, steer, or absorb sound in ways that nothing found in nature can. So how exactly do these structures pull it off? How do they create the physics of silence? Well, it really boils down to two super clever ideas. On one side, you have something called Bragg scattering. This uses a perfectly repeating pattern, kind of like a picket fence, to bounce away high-frequency sound waves. But the real game changer, the thing that gets everyone excited, is local resonance. With this method, the material has all these tiny resonators built right into it. They act like microscopic tuning forks that vibrate at just the right frequency to absorb sound energy and trap it. And here's the kicker. This lets them stop that stubborn, low-frequency sound using a structure that's way smaller than the sound waves themselves. That's the part that's so revolutionary. And you can see these two ideas right here. On the left, you've got a pretty straightforward repeating honeycomb pattern that's built for Bragg scattering. But then, look at the design on the right. That complex Taiji-inspired shape, that's not just a cool pattern. Each one of those is a tiny, complex machine, a local resonator, built to vibrate and just swallow up sound energy. This is where the engineering gets incredibly creative. Now, you're probably looking at these intricate shapes and thinking, okay, that's cool, but how on earth do you actually build that? For a long time, you couldn't. These were just ideas on a whiteboard. But then a manufacturing revolution changed everything. For decades, the math said these structures would work, but our tools just couldn't make them. You couldn't use traditional methods like casting or milling to create something with such a complex inside. It was physically impossible. And that's where 3D printing or additive manufacturing comes in. This technology allows us to take these wild digital designs and bring them into the real world. You design the complex part on a computer, the software slices that model into thousands of paper-thin layers, and then a 3D printer just builds it, one precise layer at a time. And the results are just wow. Look at this thing. It's called a triply periodic minimal surface, or TPMS. It is a perfect example of a geometry that is both beautiful and incredibly functional. It's the kind of thing that was impossible to make before. 3D printing was really the key that unlocked the full potential of metamaterials, taking them from pure theory to physical reality. Okay, so we can design them, and now we can build them. But what's the payoff? What can we actually do with them? Well, this is where the technology starts to sound like it's straight out of science fiction. The applications are already starting to pop up everywhere. Imagine super thin, feather-light soundproofing for airplanes and spacecraft, where every ounce matters. Or get this, coatings that could make a submarine acoustically invisible to sonar. Back on land, they could be used as barriers to stop buildings from shaking when a train goes by. And in medicine, they're developing metamaterials that can actually cancel out the distorting effect of the human skull, which would let us get unbelievably clear ultrasound images of the brain. It's just incredible. This core idea that you can control waves just by designing a material's internal structure is so powerful. And of course, it gets you thinking. If we can do this for sound, what else is possible? This quote from the research really just nails it. This isn't just a slightly better version of soundproofing, it's a fundamentally new way to think about controlling sound waves, and it's opening doors to technologies we are only just beginning to dream up. So, we'll leave you with this final thought. The principles behind metamaterials controlling waves through structure are universal. Today, we're talking about sound, but what about tomorrow? Could we use the same design philosophy to create thermal cloaks that can hide or direct heat, or build optical devices that bend light in ways we can't yet imagine? If we can engineer a material to create silence, what other fundamental forces of nature are just waiting for us to shape them?